welcome to, what is this, Fall 2017 Senior Seminar for Chemistry. Today's presenter is Zach Felkel, and he'll be talking about that, which primarily is graphene aerogels. I'll let him tell you the rest.
Thank you. Yes, as Dr. Luce said, our seminar this semester is about biomimetic architecture graphene aerogel with exceptional strength and resilience. The objectives to guide our way through this presentation include what an aerogel is, the synthesis of aerogels, significance of the highly ordered architecture that makes the aerogel, this aerogel, what it is, strength and strain, and applications. An aerogel is a solid material with extremely low density produced by removing the liquid component of a suspension of a gel. Various types of aerogels include metal oxide, silicon, and what I will be concentrating on today is graphene. So uses of aerogels include catalysts, which, being that the aerogel is carbon, it can act as a catalyst because it has such a surface area and can react with many parts of the mixture that it's in. Graphene is a good conductor. As illustrated over there, it is in that image. The p orbitals all bind together in a bonding formation, and it has delocalized electrons. So an electron is not restricted to being in a specific p orbital or a specific carbon atom. Aerogels are good insulators because of the empty space within it and pollution control. Aerogels can interact with the atmosphere similar to as a catalyst and let certain air or pollutants get trapped in the aerogel or not through the aerogel, and air can flow through. So graphene, the way it can be made is starting off with graphite. So graphene is essentially one layer, specific layer of graphite, and that can be gathered through starting with a block of graphite and then oxidizing that graphite, which separates the layers of graphene, and then you have then graphene oxide. You exfoliate it to separate it from the block of or chunk of graphite, and then you have a single layer of graphene oxide. You reduce it, which pulls most of the oxygens off of the graphene oxide, and then you are left with graphene. So properties of graphene aerogels: low mean free path of diffusion. So in other words, it is suggesting that the aerogel is very porous. So when air molecules, for example, in diffusion, go into it, there's another path through the aerogel that another air molecule can go into and then bump into each other. However, it has a long mean free path of electrons. As mentioned earlier, the p orbitals are all flat across the top, so electrons can go skating across the p orbitals, and that causes very good conduction, as mentioned previously. The mean free path is the average distance traveled by a molecule between collisions with another molecule before scattering. And the way graphene electrons make a great conductor is because it has the wide open space of the p orbitals that it will not bounce into another electron. And it is actually on the level of a superconductor at room temperature. So normally superconductors have to be chilled because of vibrations, of intermolecular vibrations, which cause collisions with the electrons, in which case you do not have to worry so much about this with the graphene. It has a high specific surface area, so it's very much like a powder, only it has structure, so it's not piled up on itself. And low sound speed, so that's essentially like insulation. The air, sound is carried through waves, air, vibrations. So as sounds go through it, it is blocked by the various pores, and the air does not move within the aerogel very well. So, biomimetic graphene aerogel. So essentially, when you see biomimetic, that just means it is mimicking biology. So in this case, it's mimicking the stem of the Thalia delbata plant. It is a plant found in South Africa, and it withstands wind very well, and that's how they decided to use it. So it has lamellae, so layers, and bridges. This is a 1 millimeter scale, whereas the graphene aerogel is a scanning electron microscope image, and that is a 10 micrometer scale. So cellular scale, and then they make it a molecular smaller scale. And the graphene oxide aerogel gets its structure through a method that uses a PDMS, polydimethylsiloxane wedge, as a cooling gradient, and that will be spoken of soon in this presentation. So factors in the synthesis of a graphene aerogel. The concentration of the graphene oxide and the concentration of the polyvinyl alcohol both contribute to the structure, as well as the ratio to each other, which that relates to the density. The PDMS wedge angle, well, if you have no wedge there, it interacts differently, and it cannot have the bidirectional cooling gradient, as it will be spoken of soon. Then you got to freeze dry the suspension to get the liquid out and reduce it. So first we'll talk about the concentration of the graphene oxide. So as you notice here, it is starting off with 0 graphene and 10 milliliters per milligram of PVA, and then it goes across to 5 to 10 to a 1-to-1 ratio. There will be a phase diagram soon that will explain that the first one here is a random architecture, because if you have just graphene or just PVA, it will not create the biomimetic structure that is desired. And as you notice here, that bridges increase monotonously and linearly as the concentration increases, and the lamellae increase and then decrease with concentration. And this is the concentration of the PVA. So starting off, the first image is that of no PVA and only graphene. So once again, it is a structure of no lamellae or layers per se. And then as the density goes up and the PVA goes up with graphene interactions, it has more structure to it. Now, the PVA and GO concentrations, these are all 1-to-1 ratios, but the density changes. So you have more of which. And this illustrates how lamellae, so when there is very little of both, it is only the layers, so they're not supported by bridges. But as you increase, it starts to mimic the Thalia delbata plant even more, because of the interconnected bridges separating the lamellae. And then also noteworthy is that lamellae increase and then decrease in the last 2 images. Very similar as before. Now, an explanation for the lamellae here is increasing and then decreasing is high density. The high density, as the ice nucleates in various positions throughout the aerogel, it is competing with itself on whether or not it should create another ice crystal, or should it build on the already existing ice crystal. And that the density blocks, so you have the graphene and the PVA blocking the water molecules from each other, and that can cause the various ice nuclei to not form or form on the existing. And so initiation of ice crystals was attempted, and that simply caused the ice to diminish or amalgamate within the aerogel. Thus, the lower the ice density, the more the nanoline. And this is the PDMS wedge, polydimethylsiloxane. And this shows the dual temperature gradients of controlling the growth of the ice crystals. The bidirectional freezing technique, because of the wedge, it can cool the suspension horizontally as well as vertically. And this causes the long-range ordered structure, as will be demonstrated here. The top is with no wedge, and notice how random and scattered the structures are. The graphs on the edge show the angle primarily of the graphene crystals, or graphene structures. And as you increase the wedge size, the structures begin to become more and more in the same direction. Thus, in around 85 degrees are all of the graphene crystals in the last image. And so, after you have the suspension with the mixture of the PVA, the graphene oxide, and water, it cools down and it has in its structure. Then you must extract the water from the suspension, or solid at this point. So the solid is frozen by cryogenic ethanol and lyophilized for more than 48 hours at negative 60 degrees Celsius. And this graph indicates what happens using the sublimation of the solid to gas. And with the pressure being at 0.4 millimeters of mercury, so here, and the temperature at negative 60, around here, it moves from solid to gas. And lyophilization uses a vacuum pump to get it to that pressure. And as it is pumping, and as the solid turns to gas, it keeps pumping, removing that gas. Otherwise, you would lose the vacuum, because gas takes up more space than the solid, and you would have issues with the water then not being removed directly and from the suspension. The aerogel is then reduced, and this indicates that not all of the oxygen is removed during the reduction process. The reduction process takes place in an atmosphere of 98% argon and 2% hydrogen. Graphene, when connected to oxygen, can have each oxygen adds a +1, -1 oxidation state to carbon. Thus, the carbon is a +2 when double bonded to an oxygen, for example. And as the carbon comes off, whether it be CO2, it will then be reduced to, when it is connected to a carbon, it is at a 0 oxidation state, thus reduced from the 2. And a hydrogen in the atmosphere, if that takes the place on the edge, it is causes the carbon to be minus oxidation state. And this diagram indicates that some of the oxygen remains after a reduction, and so graphene is different than reduced graphene because of this. And a way to get graphene would be chemical deposition, so going from gas to solid. And then this is an image of before it is reduced, after it is reduced. Notice how there is some warping done to the structure because of the removal of the oxygens. So it does not mess with the structure in the sense of how much it can support, or it doesn't like change the structure. It just warps it per se, and that is showing on the end there a model of that. And the graphene oxide and PVA interact with each other. So when you have PVA and you introduce graphene to it, the graphene goes and sits in between the PVA, and there's H bonding that interacts between the PVA and graphene. And then the water is introduced, or it is introduced into the water, and then the water separates the GO from the PVA. And so when the water freezes, ice crystals, and it grows in between, enucleates per se, and then the graphene is separated, breaking around in ordered structure, and the water has room for ice nucleation. So the significance of the highly ordered structure, stress distribution, and high strength and strain recovery. Think of the bridges as springs and the lamellae as a platform. You put something on it, and it's like a bed frame. It takes up, then you take it off, and it springs back. And graphene aerogel, this one in particular, can withstand 6,000 times its own mass and recover after 100 cycles to 85% of its original size. So strain recovery, the first one here is under 50% strain. So each time they have a press, hydraulic press, and it squishes the graphene to 50% strain. And up the side axis here is the kilopascals, how much force the machine is putting to squeeze the graphene. And on the bottom here, that is 90% strain. And notice how here on this graph, you see that the random, which is outlined here, this is random, that is biomimetic, the random is the red, and it does not recover nearly as well as the graphene aerogel does, even after 100. And then here, they both start at the same place, so they're both just as thick, but the random breaks down. And this is an after look at, this is a scanning electron microscope image of the graphene aerogel after the compressions. Notice how this has no obvious changes aside from minor fractures in the bridges, but that's, I mean, as noted in the graph, that doesn't make much of a difference because there's so much support there for the aerogel. In the bottom here, there are no bridges per se, it's just a matrix, a random matrix of pores in the solid. So no ordered structure, it causes cracks and breaks structural damage. So the first here, E is 5 to 5, F is 8 to 8. These are GO PVA ratios. So density is going up as you go across. So once again, they are undergoing 50% strain. Each aerogel cube is undergoing 50% strain. And this is showing that here, the lamellae increase. You're getting more and more lamellae as indicated by this image. And they decrease here by the end, showing. And also, it is noteworthy to show that the scale changes on the y-axis. That is saying that naturally they are more dense as you add more GO PVA material. Thus, naturally, you can conclude that it is harder to squish, and it takes more force to squeeze more material. However, they do not always bounce back the more dense they are, as indicated in the graph. And this is 8 to 8 GO PVA milliliters per milligrams of material. And the strain recovery ratio. Right here, the dots indicate the lamellae, so notice they're increasing and decreasing as above, and the bridges are increasing monotonously. And as previously noted, when you recall the GO graphene oxide versus polyvinyl alcohol compositions, when you have only polyvinyl alcohol, you have the random structure, and only graphene oxide, it is random. So the PDMS, polydimethyl siloxane wedge, is not the only contributing factor to it being a biomimetic versus random architecture. And lamellar, recall the graphene oxide, it had minimal PVA and no bridges, so lamellar is just the layers with no bridges. And biomimetic, that is what we were shooting for in this series of tests. So, graphene can be used in many ways. Graphene aerogels can be used in many ways, but the purpose of this, using its conductivity in actuator sensors, batteries, supercapacitors, and flexible electronic devices, flexible since it can remain and keep its own shape and resist changes. For example, it would be great for a button that you press, as we will see it in a few moments here. If you press the button, it lets current through because it's compressed, and when the button lets up, it's a phenomenal insulator, and it will resist and buffer electrons running through it. As here, this is the button idea. You have two plates of electrical current. Notice how the LED, illuminating diode, is not lit up when the graphene aerogel is touched. But as it compresses, the conduction and the current increases. So this is the strain and the stress going through, and that is related to the conductivity. The more strain there is, the more conduction it lets through, and the less strain, the fewer electrons it is letting run through. And the cycles, that is suggesting that here you have 1,000 ohms, about 1,000 ohms of resistance when they're just touching. But then as it compresses, the resistance goes down, and it is on the level of a room temperature superconductor. So this chart shows comparisons of various densities and the recovery. Notice how once again, the lamellate increase and then decrease, and the recovery ratio is at 95% at 8 to 8 ratio. Note, recall from previous slide that the 8 to 8 is the ideal as far as recovery. And notice how as the density goes up, the stress also, it can take more stress, but it will not recover as well. And essentially, biomimetic graphene is better than other. So indicated by the squares is various other porous materials, not specifically aerogels, but also inclusive of aerogels, and their strength and strength recovery ratio. Notice how this biomimetic graphene aerogel is exceptional in comparison to them, as well as here with their strength recovery ratio and strain recovery ratio. So they are stronger. Do you have any thoughts on the presentation?
Okay, other porous materials. What are some examples of things that aren't aerogels?
I'm not sure if specifically listed here, but sponge, for example.
Okay.
It's not aerogel, but I don't know if it would stick. But you know, they have metal oxides, silicon
Okay.
oxides.
Is this, are we opening the floor for questions?
Yeah,
Okay,
yeah, that was,
okay,
that
all
was, sorry, question.
Polite way of saying, any questions?
Yeah.
I'll do the segue then, okay. You're talking about exfoliating single layers. How do they exfoliate a single layer of graphene?
I'm not sure about that. I don't know if it was filtered. I just know that the oxidation of the graphite put enough space, I believe, in between the layers that they could pull through methods, pull a layer off and reduce it and have them graphene.
And then you talked about reducing the graphene oxide to graphene. How do you do that again?
In a chamber of 98% oxygen and 2% hydrogen at 800 degrees Celsius.
Okay, all right. So now you have
Did you
this.
say 90% oxygen?
No, sorry, argon. No
Argon.
oxygen.
Okay.
No oxygen.
Yeah,
Because
okay.
well, you can't reduce.
Yeah, no, that's
Oxygen.
good. That's good.
That would
I think you have a
oxidate.
fire on your hands, but
Yes.
okay. So looking at things, there are people who are looking at using graphene oxide for desalination of water, for example. And one of the things they ran into was the swelling.
Yes, I was
Okay.
reading that in your article.
Right, yeah, associated with it. So I guess in this case, if you're removing the water, you're not worried about swelling of your aerogel?
I mean, this one specifically?
Yeah.
I believe that is why they freeze dry it, so that way they don't have to worry about it.
Okay.
Because as you pull away the gas, that is why it's in vacuum, so that way it doesn't maybe swell because of the gas then
Okay.
raising the pressure from salt.
So while I'm on a roll, I got two more questions and I'll stop. Okay. Okay. That brings up the point, bidirectional freezing.
Right.
Okay. How's that different from
From flat, random?
flat freezing? Right. Random freezing.
Well, care if I go back to the...
Please do.
Alright, so the ice crystals are indicated by the white and the temperature gradient. So it's the ice crystals are growing up through the lamellae. So the ice crystals separate the lamellae, and then as they grow, the bridges then are deposits of excess graphene that cannot be added to the lamellae. So the bidirectional, then the higher the angle, we noticed in the next slide, the more compressed and ordered the ice is. So as here, you know, it's just random. The graphene is in the ice, the water is in the solution, and it's just all freezing, no direction, no order to it at all. Just whenever ice wants to nucleate, it does.
So you don't get good structure that way.
No, no.
Right. Okay.
Zach, can you show us on the pictures, those pictures, how we can see,
This,
what you mean?
well,
If we don't know how to look at that picture?
or the graphs, or
Either, both.
well, here, notice how these angles are going like this, at this angle, and that is so think of an axis here, that is around 85 degrees, whereas this is flipped this way at around 120 past the axis, and that is around 90. And I believe that the ice crystals would be pushing, the higher the angle, the more it pushes the graphene together, and it causes it to lock in place, because you know graphene has a very ordered structure in itself, but as you stack graphene on top of each other, it can be random, or you can stack it more ordered, like graphite would be stacked with graphene on itself.
So are you suggesting that in that bottom quarter picture, essentially all the angles are the same?
Yes, yes. It's not clear from back there.
Right.
I
But in the second one up, some of them are going this way and some of them are going this
yeah,
way.
they're crosshatched.
But in the third one up, there's a number of different directions that they're going, and in the top one, they're just going in every which direction.
Correct.
Okay. And so that's why your little graphs over here
They're showing
have
what
angles,
angle.
have the angle on the horizontal axis, and what's on the vertical axis?
Percent. So this one has right here 55% are at this top angle, and so then this percent is at this angle.
So there's only basically one angle that they're
Essentially.
really close to one angle. But in the next one up, there's two different angles.
Mhm.
As shown in the picture, that there's some that are pointing this way and some that are pointing this way. And the one up above that, there's three different angles. And
Correct.
okay, I get it.
And you know, of course, the top one is just a jumble.
Now, these wedges, how do they make the wedges?
It is a polydimethylsiloxane, and it is a mixture, and it is poured into a mold, and it is then solidified.
Okay, so the mold basically determines the angle.
The mold gives it the angle, they pop it out, and then they put it into a container or whatever, or a reservoir, and then they pour the suspension, the polyvinyl alcohol, graphene oxide on top of it, and they cool it cryogenically with ethanol. Now, with that stated, the wedge causes the bidirectional freezing technique, and they mentioned how it conducts the temperature through the wedge. So the wedge is essentially the only cold thing, and so I guess
if you go back to your previous one,
this one.
so the wedge is that thing is going back towards the back.
This right here, yes.
Okay.
Okay.
Down.
So that's literally a chunk of plastic on the floor of this thing.
Mhm.
And the cooling stuff is on the bottom underneath the wedge. And therefore it's colder towards us than it is towards the back. Is that?
That's what I had concluded. They said it was cool with, you know, negative 60-degree cryogenic ethyl alcohol, and it freezes through the wedge. Like the wedge conducts the coolness from it, and
So is the wedge at different temperature, or is the wedge all the same temperature?
well, I would believe it would be at different temperatures with the delta T, as it's different temperatures as it goes up the suspension, but naturally that's through the process, and it will be, by the end it's all solid, it'll all be at the same
Okay, so
temperature.
it's cooler at the front, as we're looking at that picture, and warmer at the back, if you want to call it that,
Mhm.
because, okay.
Because the wedge is actually like an insulator, I think.
Yeah,
Okay, so then in your picture, what are the white vertical?
That's the ice crystals.
Then what are the blue things?
That would be the graphene oxide PDA suspension. Notice how, you know, you would have I would assume that these are lamellae, 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 and then the ice crystals growing through. And then as it builds up, as you have excess graphene oxide, it then deposits into bridges as it grows.
So the white walls in there are ice?
Yeah, nucleation of the ice.
How do you,
growing through.
so are those there to begin with, or is those forming as the process?
That is forming. So you have a suspension before you even start cooling, and then the ice crystals nucleate in those locations and then grow.
So what makes them crystallize in layers like that instead of just the whole thing crystallized?
I'm not sure about that. I mean, it is attributed primarily to the wedge causing the ice.
Can you show that or compare that to the pictures that are showing the structure and all the bridges and everything, and so we can see how, yeah, any of those.
This?
Those
Oh,
or
that's
even
the
back to
plans.
previous ones.
Here?
So on there,
Right.
so where you've got, can you talk through what those are compared to what
So-
the other pieces are?
These are, so this is the random, naturally. So you have the ice crystals just, so void space. Essentially, what I've concluded is void space is where an ice crystal was. So you have the nucleation, and it grows. The ice crystal grows, it has more water attached onto it, and also freeze. Now here, naturally, void space. And since lamellae are sheets of graphene, you know that the ice crystals grew. So in the article, it suggested that it was tested perpendicularly to the way it was grown. Stress test. So that means if it's perpendicular to the way it was tested, flat sheets going this way, it was grown this way. So you have the sheets going straight up and down of lamella. So the ice crystals are growing straight out at you or into the board, and then it deposits. So this one never touches this one, but it grows around the
So the white line across on that middle picture,
yes, is
show me where that is on the previous freezing picture.
here?
Yeah.
That would be this. So notice how this is turned perpendicular to be stress test, but these are the lamellae.
So then the stress test is squeezing it this way
Yeah,
on that
only
picture.
on this picture, yes. Perpendicular to the order of growth.
Can you talk about how the angle affects how many lamellae there are then? And or how many bridges there are?
Yeah, so the angle,
The angle of the wedge.
so this.
No, the angle of how big of a wedge you're using.
Yeah, so a 0-degree wedge,
Okay,
so flat, is random, and as you get more of an angle, it raises it up, and I believe it would compress the ice crystals, if not cause the difference in cooling gradient, and cause it to grow. Is that?
Is it related then, you showed other pictures where the densities and the different things have different amount of layers.
Yes.
Is that related to the angle too?
Well, I'm not sure about that, but I can relate that to, so the angle of the wedge increases the order of the layers, whereas the density increases and then decreases how many lamellae there are.
Oh, so the PVA to the GO ratio is what determines how many lamellae there are?
You
Or
go forward in some of the pictures where you have the comparisons. Or maybe not.
Or there's a table, or right here.
Okay.
So you have, so the bridges naturally increase as the density of the sample goes up.
Why?
Because the ice crystals can't grow due to competing for space. You know, they can't find each other to grow, so it has to deposit that matter somewhere. And okay, so I think what you're asking is, why don't they just create more lamellae? Because it's the and decrease. So the lamellae, I believe, take up less matter, less space than the bridges. So it's increasing because you're getting more ice nucleation, but then it decreases because you have more ice nucleation, but then that ice then amalgamates with the graphene and takes up bridges because there's more empty space in between the sheets of lamellae for bridges to form, and thus matter is going to form in the empty spaces due to empty spaces.
okay, that maybe this would help. I don't know. Can you tell us what the PVA is doing?
The PVA?
Is it in the final thing after you've evaporated off freeze dried off the water?
Right.
In the
Does
final
the
gel,
PVA
is the
remain,
PVA
or-
still there? Is it the posts between the layers, or where is it?
I'm
Or
not
does it disappear?
sure about that. I don't know if it goes with the water because, in the name graphene oxide aerogel or graphene aerogel, there's no mention of the PVA. So I am uncertain as if it is freeze-dried with and removed as the water is, but I know it plays a bit of a role in the H bonding of the graphene oxide and water,
Okay, so-
causing space for ice.
So if you go to one of your little basically cartoon pictures where you have the layers, I think in blue, and then you had posts or,
Here?
no, to actual picture, 3D pic, keep going backwards. No, the other way, towards the front.
Oh, this is the front, so first slide.
There, that one right there.
Oh, okay, perfect.
So you see the blue layers, and then orange.
Orange are the bridges, blue is the lamp.
What are the bridges made of?
That's all the graphene. It's the
So
bridges are
it's
the
also
same.
graphene?
Yeah, the bridges are the same composition as the lamelate, because it can't exactly pick out what it makes the bridges out of if it's all just one suspension of graphene PVA. So I think it is a mixture of graphene and PVA in the funnel.
You're essentially using the ice to get the structure that you want. That's
Yes.
why the bidirectional freezing is important.
Mhm.
But, okay, if you got polyvinyl alcohol, it's a polyhydric, substance, so it's gonna hold water. Is the PVA there to hold the water? So that it, essentially, I don't know if it structures it or whatever you wanna say.
I'm glad you mentioned that, because notice how here in this, the PVA and graphene, the PVA is blue, the graphene is red, and the PVA holds the water in between the graphene, thus giving it the structure, making the graphene in the structure that it is. Now, do you mind me asking
Mhm.
if PVA is a liquid at room temperature or a solid?
You guys know this because you have worked with PVA a lot. Actually, literally have worked with it. Specifically on Science Day. That's the stuff that you make slime out of.
Okay,
So,
so that's when you were mentioning water retentive.
yeah, so it's PVA itself is a solid. It's just like the white powdery stuff. You put it into water and it forms a gel.
Okay.
So it's like syrupy, real syrupy.
Yeah.
And then you add the what is it? The borate,
Borate.
sodium borate to it, and that's when it sets up like Jello.
Yeah.
But PVA in water itself is a slimy, liquidy stuff.
We used to use PVA as a binder in some of our explosive mixes for that reason, because it essentially it does hold just exactly the right amount of moisture that we needed to have. I was going to mention something else.
So it makes sense that the PVA
Would remain
is it.
in with the graphene in the structure.
Yeah, I can't see why the PVA would just disappear. So
Right.
I think it's still got to be there.
Yeah.
In fact, I'm suspecting that it's the bridges, but I could be wrong about
Boy,
that.
that's what I'm thinking too. Maybe that's how so it holds the water. I guess it's an interplay. You need the ice formation.
Well,
Especially, Zach, since in your pictures, go back to where you were a second ago.
here, this is, right here, this is lamellar
Right.
on the phase diagram. It has both graphene oxide and PVA. It has no bridges, it's just lamellae, and it's a mixture of both graphene oxide and PVA. So that's what makes me think that's a solid structure. is-
Okay, so in your lower ones where you have the kind of hairy stuff in between,
That's the bridges.
right. And that's graphene, you think?
I would say it's the same composition of the lamellae, depending on what the lamellae is.
It seems like as the ice is growing, it needs to take up the space and get rid of everything. And
So-
it almost seems that I was,
It's like a snowplow going through the streets, pushing the stuff on the
but
driveway.
at some point it can't
and-
push it away anymore.
Right, so that's where a bridge would form.
And that's what I was kind of trying to get at before is, as you've got different ice crystals growing, the angle determines how close the ice crystals grow to each other.
Correct.
So that when you change the angle, you get more or less ice crystals, which means they have to push more or less graphene out of the way. And you get different amounts of bridges based on how much it has to try to push out of the way.
I can see
Seems
that.
reasonable. Does that make sense at all?
Yeah. Can I go back, because I'm still stuck on this whole PVA and
Yeah.
where is it in the end?
This?
Yeah, that and, okay, so notice, and this is just kind of I'm trying to psych out the researchers and the pictures that they've made. They've made the levels blue,
Right.
but the bridge is orange.
Well,
Now go back to the structure,
Back to this structure?
the one that showed the chemical structures, the PVA, the blue. Blue
Do they
zigzag.
match the colors? Do you think they're matching the colors?
Remember the blue zigzag one and the,
Oh, they are from,
that one?
yes,
Notice the colors they've used there?
this is from a different source.
Oh,
than
okay.
The PVA structure itself. I
Okay,
believe
then I'm totally wrong about that.
in this one, they use different colors because if you use blue, you wouldn't be able
Right.
to see those.
Okay, so then, do you know, this is a different question, totally different. Do those bridges extend forwards and backwards, or are they like, more like wall, are they more like walls, or are they more like posts?
I believe post because they mentioned springs. Otherwise, if the bridges were all the way through, it would be 2 layers of lamellar, and it would be lamellar X direction, lamellar Z direction,
Yeah.
or 2 different
Right.
axes. Kind of like a
Okay.
bed spring.
I'm still mystified about what happens to the PVA and the, where is it in the end? Is it still there? Because it can't just evaporate, it can't just disappear.
Right.
So I don't know.
I think it would be incorporated in PVA, polyvinyl alcohol, contains oxygen, maybe.
It's only
I've got
having
a
reduction.
suggestion. In the
Stop.
reduction here, we have, oh, I passed it. A moment, please. Right here. Not all of the oxygen is gone after the reduction, and possibly, if the PVA is combined in with the graphene structure, it is warped after the reduction, so maybe the PVA, the oxygen part of the PVA, comes out.
I have no idea, but just,
So,
it's a mystery.
I'm reading another, this is another paper, they use hydroxyapatite. Now,
That's what your teeth are made of.
exactly, yeah. Well, they compare it to structure, to rigidity in bones and teeth and different things, so they use, um, instead of polyvinyl alcohol. Gels are
Hmm.
fascinating. I haven't read the whole article, but.
Okay, so on a different subject, I have another question. Can you talk more about the redox reactions and the stuff that's going on there with the, I guess you're reducing the graphene oxide to graphene, but it's not exactly like regular graphene.
Right.
So can you
because
talk about the reactions and the redox oxidation numbers that you were trying to outline?
I'm not sure about the, what do you mean the oxidation numbers? Like, so carbon, each oxygen on the carbon raises the carbon's oxidation number to, if it's connected, like CO2 for example, would be +4. The carbon would be +4. Is that
That's
because
right.
it's double bonded to each oxygen?
So what's happening in the reduction? I'm assuming hydrogen is a reducing agent.
Right, or in the high temperatures being very high centigrade, it breaks down the structure itself.
So do the oxygens turn into water? Does the oxygen get reduced to water?
What's changed as
I wouldn't say
you're
that.
heating it up with the hydrogen
Yes.
and the argon? What's happening chemically?
I was under the impression that the carbon would come off, or a carbon would leave with the oxygen. Now I may be wrong in my science here. Have CO2 escape, and then have the open bond there that is left replaced with a hydrogen, thus reducing it. But naturally, it would also be reduced if it was just left.
What could the hydrogen be doing? I don't think carbon's leaving.
Although there was one slide that seemed to show there was a CO2, which surprised me.
Yeah.
Do you know which one I'm talking about? There was a slide that had.
Yeah.
Yeah, that seems weird to me too.
That's why I thought it might be a little more complicated than it seemed.
Here? Oh, no, here.
Here,
That one.
There.
Yeah.
No, that's not a CO2 leaving.
Oh, is that a water?
Yeah. The colors aren't.
What is the blue color and the orange color representing there?
I thought this is, once again, another source. Sorry.
Okay, that's okay.
Confusion. And I believe this is the graphene, and then these are hydrogens, and the oxygens there from it being oxidized initially, and then they come off with the other, thus causing the warped structure.
So
that
what's,
was mentioned.
what does the blue represent and what does the orange
The
represent?
blue would be the carbon, the red would be the oxygens.
Okay, so that does suggest CO2.
Are you sure that's what they said, or are you just speculating that's
They
what the
didn't
colors
say
are?
in the article what
'Cause I don't think
happened in
that's
the
what-
reduction process.
Wow.
Because that's really not an oxidation.
The
I mean, it's sort of an
reduction-
internal redox reaction.
Yeah,
If
it's-
CO2 is
They
coming.
didn't concentrate on the reduction very much. They just said it was thermally reduced, and then you go to the methods and they mention the specifics of the high temperature and the atmosphere.
Yeah, but of
Yeah,
course,
that's-
as chemists, that's the part we're interested in, is the whole chemistry thing.
Right.
The hydrogen is gonna go in and rip off the oxygens. That's
So
what's
you
gonna
get
happen.
water.
Mhm.
It would seem like, that's what I would have thought too,
The
but that slide
hydrogens
suggests.
go in as 0, they get oxidized to +1 with the water.
And then the carbon would then bind to
The
itself again?
the oxygen gets pulled off of the carbon, the oxygen stays -2 the whole time. And as the hydrogen pulls the oxygen off, the carbon is reduced back down to 0 because it doesn't have the oxygen in it anymore. So the hydrogen is being oxidized, the carbon is being reduced, and it's happening by stealing oxygen.
So then the carbon then has that open spot to be double bonded to another carbon.
And that's how it gets the chain, the
That's how
graphene
it gets
chain.
there. Okay.
Now that all
But
makes,
that picture doesn't
that's
seem to
exactly,
show that.
that's exactly what I would have thought, but that's not what the picture shows. The picture shows CO2 coming off.
If that's right, but he's not saying that for sure that that's what they said the colors
Well, if the
were.
blue, if the blues are,
But I asked you,
Carbon.
you said you were sure, the paper didn't say the blue was carbon, did it? Did
Right.
the paper address what the colors were?
but the blue has to be,
Assume that's what they were.
the blue has to be carbon because there's so many of them.
Right.
Unless it's just blowing up a picture where the white is the carbon and the blue is the oxygens on the carbon. I don't know.
Once again, this was from a different article about that illustrated 4 methods of reducing carbon, and this was illustrating the thermal reduction part of which, and it matched.
So if it's a different paper, it's not, that might not even be a graphene layer there.
It is.
It is?
Yes.
Okay.
It is an oxidized graphene.
I mean, I guess it could, I mean, that would be a reduction of the graphene. The carbon that's coming off would be oxidized and the carbon of the graphene would be reduced.
If it's actually pulling carbons off.
But then you don't need the hydrogen. So,
Yeah.
so, anyway, it's interesting that, I mean, that reduction step is the interesting thing to me.
I don't,
I had one more comment, sort of, go ahead, Mr. Pickup, what were you going to say?
I'm thinking out loud, the auto, what is it, auto ignition temperature of carbon? I mean, you got it under an argon atmosphere, but hydrogen there, something,
Yeah, something's not right.
something's not right.
It doesn't seem like enough hydrogen for the hydrogen to be ripping all the oxygen out either.
Depending on how much oxygen there is, and we don't know
Exactly,
that.
yeah.
So that little picture up there, I think, is interesting, because you're literally showing the gel itself, the aerogel.
From a amber color to black.
Yeah. Do you know, once it's done and you have your chunk of aerogel sitting there, do you know what its density is? My impression is it's really,
It
really,
varied, actually, as the suspension would.
it would vary with the number of lamellae, I would guess.
Yeah,
Do you know
and the
roughly?
suspension, the precursor.
Mhm.
So, in the suspension, I'm not sure about final. It is not very dense at all, but the precursor was 8 to 8 milligrams, milliliters versus to milligrams as a precursor. But I'm not sure about the final.
Right.
After,
My impression of aerogels in general is that they're really, really, really light.
yes.
You could pick up a whole room full of it basically with, just by itself, without any levers or anything, just pick it up.
Mhm.
So light.
It cannot be too massive because there was an image, I didn't put it in the PowerPoint, of a centimeter scale graphene holding 6,000 times its own mass, and it was a mass about like that big. So 6,000 times is that large of metal. It can be too.
Yeah. Aerogels are fascinating things. I've seen a picture of an aerogel sitting on a tabletop with just a chunk of it, and it kind of looks like a cloud. It's almost like invisible because it's so not there. It's essentially all just air.
Much empty space.
But it's really strong, so you can't push on it. It doesn't really depress much. So they're really cool. I'm surprised that one is so dark, basically. I guess it's because...
Possibly because I was also looking online. The silicon ones seemed to be more white, whereas carbon, graphene...
It makes sense that
black.
Graphene is black, yeah.
But I'm not sure as to what the color change. I did realize oxidized graphene would be an amber color. That threw me off. But
Yep, kind of makes sense. And then the last thing I have to say is sort of in question, in answer to Mr. Pickett's earlier question about how do you exfoliate it. I know, I'm not sure how they did it in your thing, but I know when graphene was first coming out, they literally took graphite, a chunk of it, and they put a piece of Scotch tape down on it, and they pulled the Scotch tape off, and then there was a layer of graphene on the surface of the tape. That's how they first discovered it. It's really cool. So I'm guessing it was something similar to that, except probably fancier. But.
Anybody else have anything? Okay, thank you, Pat.
No, but I remember the present.